Please listen carefully.
Hello and welcome to GasGasGas, your one-stop podcast for the FRCA primary exam. This podcast will fill your brain with information. Listen to it, think about it, and check out the show notes on the website. There you will find the core diagrams you need to be able to draw and describe for the exam. This podcast can squeeze into your day. Listen while you're driving to work, cooking dinner, maybe when you're on call, or in the gym. Eventually the revision is going to end. But for now, expect facts, concepts, model answers, and the odd tangent. Remember to rate and follow the show to hear much, much, much more. So, Tom, welcome to your second recording session of Viva Practice. How are you feeling today after your Christmas period?
Well, I haven't done quite enough work and then had the scares put on me by a mock exam scenario that we did yesterday in Chorley, but other than that, fine.
Did it all go badly or was some stuff good?
The OSCE stuff went well, to be honest, and the clinical things went well. There were a few old gaps in the SOE stuff.
All right, well, hopefully we will find them today.
Well, maybe from your point of view. Schadenfreude.
Yeah. Are you ready then, Tom?
Yeah, ready when you are.
Nice one. So, Tom, what is a vapour?
A vapour is a state of matter where a gas is formed below its critical temperature and it can exist in equilibrium with its liquid state.
Okay, tell me a bit more about this equilibrium with a liquid state.
So, if you imagine a liquid containing a single substance in a fixed container, a certain number of molecules will reach an escape energy and evaporate from the surface of the liquid and form a gas, and some certain number of molecules per unit time will also form a liquid from the gas itself. If left to reach a state of equilibrium, for a given substance at a given temperature, you'll reach a standard pressure above that liquid, which is known as the saturated vapour pressure.
Ah, lovely. Moving on from saturated vapour pressure, what's the difference between relative and absolute humidity?
Relative humidity for a given temperature is the percentage or the decimal fraction of the humidity at the saturated vapour pressure. Absolute humidity is a measure of the water vapour content of a gas by mass per unit volume.
Okay. So, you've mentioned vapours in a single container. How does a vaporizer used to deliver anaesthetic gas differ from this simple container system you've described?
So, the way it differs is rather than being a closed container, there's a flow of gas through the vaporizer to allow uptake of the vaporous anaesthetic agents into the anaesthetic breathing system. The way it achieves this is by having a single limb within the system that passes gas through the vaporizer. This reaches its saturated vapour pressure, which is important because that gives a known partial pressure of the anaesthetic agent within that mixture. That is then added to the main flow of gas into the anaesthetic system at a particular ratio, which will give you a known concentration of the anaesthetic gas being delivered to the patient.
And what things can influence this concentration that vaporizers compensate for?
So, as vapour evaporates, that's a process that takes up energy known as the latent heat of vaporization. So as the gas evaporates, it cools the container and the system within which the vapour sits. At lower temperatures, you will have a lower saturated vapour pressure, so this can alter the partial pressure of agent that's being delivered to the anaesthetic system. This can be compensated for in different ways, but most typically by a bimetallic strip, which alters the splitting ratio, so essentially alters the portions of gas through the vaporizer and through the non-vaporized part of the anaesthetic machine. I can explain more about how bimetallic strip works if you'd like to know.
No, that's okay. So if we were to compare a sevoflurane vaporizer and a desflurane vaporizer, what are the key differences?
So desflurane encounters specific problems because of its low boiling point. At around room temperature, we're close to desflurane reaching its critical temperature and therefore not delivering a predictable amount of anaesthetic gas into a vaporizer system such as the one used for sevoflurane. The way this is overcome is by directly heating the desflurane to give a predictable concentration of desflurane that's injected directly into the anaesthetic system as a separate jet. It's known as a Tech 6 vaporizer, which has this specific ability.
Okay, so it sounds like heat plays quite an important role in how we deliver volatiles to patients. What laws govern the movement of heat between different elements of a system?
So the second law of thermodynamics, hang on, I'm just going to pause and think for a moment there. So there are two separate concepts that are important to understand for transfer of heat. There is the temperature of a substance and the concept of heat itself. The temperature of the substance is the essentially the thermal state of a substance, which tells you about its propensity to give off heat or receive heat to its surrounding environment. Heat itself is measured in joules, so it's actually just a measure of energy and reflects the amount of energy contained within a substance as heat. In terms of temperature, that's measured on a separate scale, so Kelvin is the SI unit for that.
Yeah, and could you define that SI unit for me, please?
The defining point of the Kelvin system is actually absolute zero, the temperature at which there is no movement of molecules whatsoever, and so they contain no heat energy. And this point is known to be at minus 263 degrees centigrade. Or 263 degrees below the freezing point or triple point of water.
Okay, yes, and what is the triple point of water?
So the triple point of water is the temperature at which water can exist in a solid, liquid and vapour states.
Yeah, excellent. For extra points here, at what pressure and temperature is the triple point of water, Tom?
So the triple point of water is 0.01 degrees centigrade and 611 kilopascals.
Oh, pascals, I think you mean there, Tom. Nice one.
Beg your pardon, yeah, pascals.
Just as a quick aside, whilst Tom thinks about his life choices here, he's probably the right one to not be so interested in the laws of thermodynamics. So there are 4 laws, although it's awkward because the first law is the zeroth law. The zeroth law asks you to imagine 3 compartments, A, B, and C. A and B are not linked, but A and C and B and C are linked. If A and C and B and C both happen to be in a thermal equilibrium, then A and B also must be in thermal equilibrium because they're connected by C. The first law of thermodynamics: in a closed system, the amount of energy remains constant. Energy being heat, sound, the electromagnetic spectrum of like radiation and light and X-rays and radio and all that jazz. the energy remains constant in the first law. Second law, in a natural system, entropy is always increasing. Entropy is a concept for the amount of disorder in a system, i.e., as energy flows from being neatly compact and tidied away and easy to use into a messy state. Imagine putting fuel into a car. You get some forward motion, but then you also get heat, you get vibration and noise, and it probably radiates some infrared radiation as well. It's much harder to gather all that energy back up. Third law of thermodynamics. The lower the temperature of the system, the less entropy is present. So if you have a box of 10 molecules, if they're quite warm, they could be in all sorts of different permutations of, they could be stacked, they could be vertical, they could be all randomly organized in there. But the colder and colder they get, the less able they are to be in multiple different states, because if they're bouncing up and down like lunatics, that requires a lot of energy. So as you get colder, they might just, be pogo sticking in one place. And if you get colder still, they might just be lead rolling around. And if you get colder still, then they're just lead there doing nothing. And that is, as you get colder, there are fewer states that the matter could take on. Back to Tom. So you mentioned critical temperature earlier. Yeah, so what's the difference between a substance above and below its critical temperature?
Above its critical temperature, gas can no longer be compressed into a liquid at any pressure. Below its critical temperature, there will be a pressure at which that gas can be compressed back into a liquid form.
Okay, so if we were storing nitrous oxide in a cylinder and Entonox in a cylinder, what bears out in the context of the critical temperatures of these two substances?
So nitrous oxide itself has a critical temperature of around 36 degrees centigrade. So within the room temperature canister, it's stored below its critical temperature. The practical implication of this means that within the tanks it's contained, there is, assuming they're below 36 degrees centigrade, there will be a fluid level, and above that fluid level, as described at the beginning of this session, nitrous oxide will reach its saturated vapour pressure, and it will do that irrespective of the volume of liquid left within the canister. This means that pressure readings that we receive from pressure gauges attached to a nitrous oxide canister will always read the saturated vapour pressure until the tank is almost empty. For Entonox, it has something called a pseudocritical temperature, and I think the strict definition of a pseudocritical temperature is the critical temperature of a mixture of gaseous elements. So this temperature is around -6 degrees Celsius for nitrous oxide. So let me just pause and think about that for a second. Yeah, so I think it is around -6 degrees centigrade. So approaching this temperature, if the canister is allowed to cool, such as in cold environments, or if gas is quickly discharged and the canister cools under the Thomson effect, then the gases can actually become liquefied and separate. This means that oxygen-rich mixture can be administered up to a certain point, and then a hypoxic mixture from the top of the canister could be delivered later on due to this separation.
That sounds like quite a bad thing.
Yet potentially dangerous and worst case fatal.
Oh, we've got a little bit of time left. It's not 15 minutes just yet. Which means I can move nicely on to the gas laws. Talk me through the gas laws, please.
Wow, that's a generous question. So, ideal gas law describes the relationship between a gas's temperature and its pressure related by the universal gas constant. So there are multiple ways of expressing the universal gas law, but the most common is PV equals nRT, which is pressure times volume is equal to the number of moles of gas times the universal gas constant times the temperature in Kelvin. Which other gas laws would you like me to discuss?
So you've sort of unified those three gas laws there. So you've sort of jumped the gun slightly. So I'm talking Boyle's, Charles and gay-lussac's laws.
So, talking about Boyle's law initially, Boyle's law tells you that for a constant temperature, there is an inverse relationship between a gas's volume and its pressure. So, the smaller the volume, the higher the pressure. For gay-lussac's law, tells you for a constant volume, there is a direct relationship between a gas's pressure and its temperature. Gay-Lussac's law tells you that, beg your pardon, we've just spoken about that. Charles's law tells you that for a constant pressure, there is a direct relationship between temperature and volume.
And I think that's actually beautifully timed up there. Well done, Tom. Take a moment, have a breather.
Tell me about the gas laws.
Hey, you know what, Tom? You were much slicker.
I happen to remember the physics stuff a little better, and that's something that was commented on yesterday, I think.
Yeah, your comfort zone, clearly. I was hoping you would tell me the 4 laws of thermodynamics as well, but I figured we'd just move on.
I started having massive doubts about which was which, and I figured that the inevitable increase in enthalpy was probably not particularly relevant.
No, but interesting nevertheless. Right, so that was more your comfort zone, is the impression had there. Is there anything that caught you out at all?
Trying to recall the gas laws on the hoof was tricky, but I have ways of doing it, which you saw me hesitating, but I have to think through some ridiculous images in my head to get them the correct way round. Also, we're doing this in an audio format. They're very much easier to draw a quick graph, those laws. So long as you label your axes correctly, I think it's much more clear what you're talking about.
Oh yeah. Would you just try and describe those graphs a sec?
Yeah, so I guess we're not under exam conditions, so I'll take a bit more time now. So Boyle's law, you'll see essentially curve with decreasing gradient from left to right, with volume on the y-axis and pressure on the x-axis, I believe.
Yeah, so the volume of gas is inversely proportional to the pressure if you've got a fixed amount of gas at a fixed temperature.
Yeah, that's right. The other two are much more simple. They're both straight line graphs, essentially. They're direct proportionality. And for gay-lussac, its volume is the thing that remains constant. And so pressure and temperature are directly proportional to one another.
Nice linear line.
Exactly. And Charles's law, it looks exactly the same, but the axes are labelled differently. So Charles's law, we've already spoken about temperature being constant, volume being constant. Now for a constant pressure, you get direct proportionality between temperature and volume.
Yeah. Maybe you've got a different way of remembering this to me. I always thought that the first law, it boils, so it's at a fixed
that's exactly how I remember Boyle's law.
And then Charles is under constant pressure to be king, but now he's king, so he's under constant
steal
pressure.
That. I also
think
that gay-lussac sounds a little bit like ballsack, and so I imagine someone with a very, very large scrotum, which helps me remember volume. You asked, James. I said there were some ridiculous pictures in my head.
Yeah, I just remember the first two, and therefore know that the third one has to have a fixed volume because that's not the one we've done yet.
Well, that's what I've been doing with Charles's law, which is why it always takes me a bit longer.
Yeah, I think maybe just rearrange those in your head. Okay, might cut that ballsack bit out. I don't know. So that was Tom after his adventure into the physics section of his Viva, where he covered vapours, humidity, saturated vapour pressure, heat, temperature, trying to do the laws of thermodynamics. I had a meander through critical temperature in Kelvin and how that's defined. They do like to ask SI unit definitions in the exam. Check out the show notes for the new definition of Kelvin. They've decided that the Boltzmann constant is a better choice. And then meandered into gas laws. It's always worth reeling off the gas laws slickly because it's just something you should know, and try and do them in order because otherwise the examiner's going to start listening more closely if you go slightly off-piste. Anyway, thank you very much for listening. You've been listening to James and Tom on the Dr. Gas VivaCast. If you found it useful, or awful, please like and subscribe and rate the show. Definitely check out the show notes for those diagrams and the detail of this content. It is a bucket of content to get to grips with. Keep working at it, and you will get better, faster, and stronger. It is vital to keep your interest live for the science that we're covering and not overcook yourself. You will be amazed by what you know come exam day. Don't freak out, keep studying.